Good morning. Welcome to week 3 of the Stanford HPC Center seminar series for fall 2021, where our focus is on Intel OneAPI tools. So the agenda today is introduction, of course, right now. Then around 11:05, we will hand it over to Varsha, who is on for discussion and presentation on Intel Compatibility Tool, then followed by a little Q&A, and we will wrap up at 11:45. The sessions coming up are Intel Offload Advisor on September 29th, followed by deploying OneAPI in one container on OpenHPC on October 6th. You'll need to register for each session. If you've been attending sessions already, you know this, you have to attend or register for each session individually using the same link. There's also the Intel On event, October 27th, 28th coming up. I'm not sure if the registration is open for that, but the link is shown there on the slide. You can also just Google for Intel On. I have a course that I offer starting October 4th through continuing studies, CS74. This is open to everyone, no matriculation, that's Stanford required. In Introduction to Building High-Performance Computing Systems, this focuses on OpenHPC and includes a number of activities related to one container and OneAPI. Videos from the seminar series are available at this, at that link there, tinyurl.com/Stanford-OneAPI, or you will be able to get them on our events page as well. If you have any questions about the series, questions that are not answered during the session, or just in general about Intel, you can contact either Jeff Rogers, who is on the line today, or myself, and our email addresses are right there. So what I'll do is stop the share now and hand it over to Varsha.
Thank you, Steve.
Sure.
So let me go ahead and share my screen. Okay, so you see my screen, right? Oh, no.
Not
yet.
Oh, it's coming. It's coming. Yeah.
There
Okay.
we go. We've got your screen
Perfect.
now.
Okay, great. So hi, everyone. I am Varsha. I am a software engineer here at Intel. I work mostly with the Intel C++ compilers. I work on enabling Intel C++ compilers on customer applications. So we work with a number of customers like from the HPC AI domain, and basically work on optimizations on Intel architecture. Lately, we have been doing a lot of heterogeneous work using data parallel C++ and OpenMP offload. So today's topic of discussion is the Intel DPCT compatibility tool. So going over the agenda today. So today's agenda, I'll have a brief overview of OneAPI. So for those of you who haven't seen the last two sessions, this is just a brief overview of what OneAPI is. And then I'll go over the Intel DPCT compatibility tool workflow and with an vector add example. Then I'll show a demo on some samples like vector add and a sample from Rodinia benchmark suite. And lastly, I'm going to talk about the best known methods from migration. This is basically just like dump of all the best known methods we have accumulated working with different apps. So let's get started. So what is this OneAPI project, right? The intent of OneAPI is to deliver a common developer experience across scalar, vector, matrix, and spatial architectures that can run on different heterogeneous systems like CPU, GPU, and FPGA, for example. OneAPI basically has two parts to it. The first one is the open source OneAPI industry initiative, and the other is the Intel offering of OneAPI Intel product. So what OneAPI is basically it sits in between your your hardware and your application. You can OneAPI has data parallel C++, which is the explicit programming language to code on your accelerators. And it also has API-based programming through libraries. So OneAPI is like a foundational programming stack, and it is used to optimize your middleware and frameworks that sit on top of it. For example, let's say AI framework TensorFlow. Then you have your applications, the high-level application on top of it, which can either be directly programmed using data parallel C++, or sometimes your applications may use these middleware and frameworks. So what the Intel OneAPI product is basically a reference implementation of OneAPI. They are actually a bunch of toolkits which are grouped together, which has different softwares. So OneAPI has the Intel OneAPI has like the compilers, libraries, and tools. So it also has a data parallel C++ for direct programming. Then we have the source code to source code porting tool that will help ease transition to data parallel C++ for developers with existing code written in CUDA. So this is the topic for today, which is the Intel DPC++ compatibility tool. Then you have, for API-based programming, you have a range of performance libraries that are included, spanning several workload domains that benefit from accelerations. So these library functions are custom coded for each target architecture. So no developer tuning is required when developers migrate code between the supported architectures. And finally, you have the tools, which is basically the offload advisor or just the advisor, vTune profiler, which help in analyzing your code to improve on performance. So this is just a flow chart to demonstrate the possible workflow an application developer may take to evaluate the next steps on how to leverage the OneAPI on the diverse set of hardware architecture. So if you already have an existing application which is written in CPU, then you can think about accelerating your application. So you can think about offload. So if you think that your application could benefit from offloading, you can use the Intel offload advisor to basically understand that if there are certain kernels of your code which could be offloaded. So if you do decide that, okay, offloading, I can see that there are some benefits of offloading my application, then you can either try to you can choose on the programming language. So you can either use a data parallel C++ for explicit GPU style programming, or you can use OpenMP offload for like compiler-driven offload. And if you find that the application probably won't benefit from your from offloading, then you can think about future-proofing your application. So today, your application might not benefit, but there are other if in future there are other architectures which come out, then you could think about using data parallel C++ to support that. If you think okay, you don't need support for multiple architectures, then you can continue accelerating your application using OpenMP or TBB. Right. Now, if you're starting with a new application development, then again, you can use data parallel C++ or OpenMP offload based on what type of. So if you're using C++, then you can use either way. Lastly, like if you are currently using accelerator hardware but are basically vendor locked, then you can use the DPC++ compatibility tool to migrate to DPC++ and start maintaining your application to support hardware from multiple vendors. So yeah, so there are different ways, or based on what you currently have, or if you're starting new, you can choose different tools from the Intel OneAPI toolkit. So yeah, today's topic is the migration to data parallel C++ and how Intel can help with that. DPCT is basically a tool that helps to migrate programs which are written in CUDA to data parallel C++. This helps to minimize time and effort when moving from CUDA to data parallel C++. So there is there's some amount of preparatory work which is required basically to identify your project, to identify the CUDA sources in your project. And then you have something called as the Intercept Build, which is a tool provided by the OneAPI. It is part of the DPCT software. It helps in basically capturing the compilation command and macros, and it creates a compilation database. The compatibility tool just migrates from CUDA to data parallel C++ using a DPCT program. Now, if you have other C or C++ sources, those remain unchanged. And mostly important thing is here is that it does not migrate 100% of your code. It only migrates about 80 to 90% of your code, and it gives you a baseline code in in DPC++ to basically develop on. Okay, and for those like for the part which is not being migrated, DPCT helps with providing warnings or inline comments as hints to help the developers with migrating the rest of the code. So again, it is a developer's responsibility to check if the migrated code is correct and functional. So as I said, it provides just a baseline for developers to start off and enhance your application using data parallel C++, and they can continually work on improving the performance and the code quality. So yeah, this is just a simple example of how the DPCT a program basically migrates a CUDA code. So this is a simple example of an vector add program. So vector add is kind of like an hello world in the heterogeneous base languages. So vector add adds elements of two arrays, A and B, and basically stores the results in a C array. So you probably would have seen this anatomy of DPC++ in your last sessions. So I'm just going to go step by step into how the migration happens. So in the first step, you have your header files. So these header files are replaced with the SQL and SQL header files and the DPCT header files. So some DPCT header files have contain some helper declarations. Then the second part is where the actual kernel happens. So you can see the vector add kernel is the kernel. So in CUDA, you have thread ID, block dim to access the individual elements, whereas the data parallel C++ has different accessing methods like get global ID, local ID, etc. There are a lot more. So in this case, as you can see, the difference is in the indexing of the work element. In CUDA case, thread ID is used, whereas in the migrated code uses the local ID. So again, the code generated is basically meant to be as general as possible to fit all possible scenarios. In this case, it uses a 3D ND range. So you can modify it to basically use 1D range in your code. The next is the memory allocation. So the CUDA malloc API is basically migrated to the USM-based SQL malloc device, which takes in the vector size and the context. Before this, you do see that the DPCT generates code for getting queue and the context. So a device is associated with a queue. The next, so next is the kernel call, which happens. So the queue is the work is submitted to the queue. And then you have the parallel for, which basically operates on the global ID and global items and number of work items in a particular work group. So once the vector add kernel is called, you need to copy data back from the device to memory. So you can use the USM-based memcopy to basically copy the memory back to the device. And the CUDA free is replaced by the equivalent SQL free in data parallel C++. So yeah, basically this is just a general idea of how individual sections of the code are migrated to data parallel C++. So usually in case of compatibility tool, we say that there are basically 3 steps. One is the prepare, where you create the compilation database using the Intercept build. Second one is the migrate, where you migrate your source to DPC++. And the third step is review your source. So basically verify your source for correctness and fix the migrated part. So these are all the slides I had for now. I will come back to the slides, but before that, I wanted to show you a quick demo of DPCT in action.
Can I interrupt real quickly for a quick question?
Sure.
So the question is for targeting FPGAs, does the interoperability tool have an option to convert it to DPC++, or what are the options to compile HLS targeting DPC++?
So we do have DPC++ support for FPGA. Is that the question?
Yes, I think one thing I'll kind of qualify here too is since that we have brought on the folks purchased the FPGA company a few years back, that we're incorporating that now with this, but it does include the tools as well. When you get OneAPI HPC toolkit base plus HPC toolkit, you do get the FPGA tools that do go along with this as well too. So if there's questions for FPGS separately, please reach out to me in my email address, and I'd be glad to set up a call with our FPGA experts as well too. We're in the process of bringing this all together, but there is some expertise in that side of the house that may be helpful for you. Sorry about that, Varsha.
No worries. Any other question? That's it, Jeff, for now. Okay. Okay. So before I go into the demo, I just wanted to point out that this slide basically to get where to understand where you can get the source code and how to run it. So right now I'm showing you the demo on my machine using command line interface, but you can also try out these examples on Intel Dev Cloud. If you are on your own machine, then you can either choose IDE or command line interface for Linux or Windows. So we have integration support with Data Parallel C++ compatibility tool in Eclipse and Visual Studio. So let me just stop sharing my slides and go to my screen. Are you guys able to see my screen?
Yes, we can. Yes, we can.
So you're seeing my SSH screen, right?
Yes.
Okay.
If you can, I don't know if it's just me or if you need to enlarge that at all, but it's visible. Might just be me.
Okay.
Might just be that I'm an old man. I don't see very well.
So yeah, the first demo I want to show is basically the same vector add program. So we'll follow the same steps as we saw, which is prepare, migrate, and review. So in case of this particular sample, you know that vector add is pretty straightforward, and you kind of know you have just one CUDA file. So what I'm going to do is just directly jump to migration. I'm going to use a DPCT directly on the CUDA file. For that, I need source DPCT. So here I have the vector add file in CUDA. So I'm just going to use the vector add DPCT on the vector add. And so as you can see, right, it basically gives you a bunch of information messages. So it tells you where the migrated code is placed. It's placed in the DPCT output directory. It's a default out root directory. You can change where you want it to be placed using the -out root option, which is provided with the DPCT. And then gives you a bunch of warnings. So basically the idea is to look into these warnings. So let's look into what what is the code which has been migrated. So let's go to DPCT output, and then you can see over here, you see a vector add file with .dp.cpp extension. So this is the migrated code for you. And then when you open it, let me also open the CUDA file. So on the left hand side, you have your CUDA code, and on your right hand side, you have your DPC++ code. So again, we have the code is pretty much the same as what we saw in what we discussed, and we discussed different sections of the code as well. So what we are focusing right now is basically on this warning. The warning is also provided as an inline comment. So if you look into this warning, it says that the migrated API does not return the error code, and 0 is inserted. You may need to rewrite this code. So the reason for this is basically CUDA uses CUDA uses error codes for error handling, and data parallel C++ uses exceptional handling using try and catch. And you can see that DPCT has already generated your try and catch block over here. Since you can, so the only modification you need to do to this code is basically remove the status return, because the mem copy doesn't need to necessarily return anything. And if there are any issues or errors when doing mem copy, then it is that it is caught by the exception handler. So this is so this is just one that in this particular code there was just one warning which it generated. Before that, and one thing to note here is that there are different types of different compile options, or not compile options, basically different options which which DPCT provides, so that you can customize the type of migrated code. So one thing which I really find helpful is, for example, the keep original code. So the keep original code basically keeps the original code in comments, and so you can see the differences between the CUDA and the migrated code. Then you can use the enable CTAD option. So basically it is the C++17 features which does the automatic template argument deduction. What else? And we talked about how the memory allocation in CUDA is automatically migrated by default to USM based unified shared memory based APIs. So if you would want to generate the buffer and accessor type of API, then you could use the USM level option and set it to none. So this would basically generate buffers and accelerators. So so I just wanted to show you a quick run of I already have it of the generated code when using enable CTAD and keep original code. Okay. So with the keep original code, you see that all the CUDA code snippets are put in comments, and then the corresponding DPC++ code is added. So what enable CTAD does is basically so it automatically deducts the type template type, so you don't need the ND range 3 in this case. So it basically does automatically deduces it from for ND range and range. So this was about vector add. I had one more sample to show, which is from the Rodinia benchmark. It is the Needleman Munch application. So, so as you can see, right, this application has the make file associated with it. So we're going to make use of we are going to make use of the Intercept build to basically prepare this source or this project for migration. So let me do a make clean. I already have a compile command. I need to remove that. Yeah, so I can do an intercept build make. And if I look into the compilation database, which is the JSON file, you'll see that it basically has all the paths to the CUDA source file, the include paths, and the compilation commands. So what DPCT does is basically uses this compilation command database. So I'm going to use DPCT on the compilation command database. So yeah, again, so here you see a bunch of warnings which are generated, and yeah, it can be a little overwhelming, but as you can see, right, there are these warnings are repeated across the same warning is repeated across different code snippets in the migrated code. We can look into the warnings one by one. So let's first go into the migrated file. So again, here you have two files which are migrated. One is the needle.dp.cpp, which is the actual kernel. And then you have the needle kernel, which is where usually you have the preparatory work and the invocation to the kernel. So let's look at the kernel itself first. And let me bring up the other one, the CUDA equivalent of it. Yeah, so again, on the left, you have the CUDA file, and on the right, you have the DPC++ file. So okay, so in this, so this is not basically, okay, I might have been wrong here. The needle is basically the kernel invocation. So let's look at the microcode which it generates and the inline comments which over here. So this talks about the migrated API does not return the error code. So we have seen this error before, and let's look at the second warning, which is the version related API is different in SQL. So what is this doing basically? As you can see that these inline comments have been basically surrounding the get CUDA driver get version. So the equivalent API for that is being replaced by the DPCT, which is the get current device. Now, and the third comment which is being inserted is about the SQL exceptions. It says the SQL uses exceptions, whereas CUDA uses error codes. So the idea behind this is, like, you can see that a single code snippet, depending upon what it is basically generating multiple warnings in different ways. So since the get driver current device and the driver version does not necessarily does not return an error code like it does for CUDA, and there are a lot of printf statements based on the error code. So we might have to change this part of the code snippet. The best way to do it is basically with just two lines of code. One is to remove your error code, because the get current device or this particular API returns a string, and then you just comment the entire line of these lines and replace it with this particular code snippet. So this one just gets the string and then displays the string. That's one, we tackled that part of the code. So now moving further down, let's see if there are any other warnings. Okay. So it's the second warning which it complains about is says that the work group size passed to the single kernel may exceed the limit. So as you can see over here, looks like the 16 is passed to the kernel as the work group size, which is well within the GPU limit. So I think this can be safely ignored. But one thing you should note over here is basically this is hard coded. The values are hard coded. So you basically would want to change that. This is coming from the preprocessor directive, so you would want to change that to use block size. Let's see if there are anything else. Yeah, it's the same thing as the previous one. Okay, so yeah, that's about it. List of warnings for this file, and we saw how to tackle them. Let's look at the other file which is generated, which is the needle kernel.dpcpp. Okay. So if you look at this file, the first thing to note over here is basically the kernel call, the kernel definition, right? You'll see that you'll have like multiple, you have 3 extra arguments which is being generated in your DPC++ file, which is the local accessor and the ND item range. In case of CUDA, the shared memory is basically allocated inside the kernel, but with DPC++, like here in this case, it's allocated inside the kernel. But in DPC++, it's basic. It needs local accessors, and those local accessors need to be passed as arguments inside the kernel. So that is why you see these extra arguments, which is basically a local shared memory accessor. And then these are just these hints are basically performance hints given by DPCT. So based on your application, if you see that it's not accessing global memory, then you can use barriers with the fence space as local space. So this would give you extra bit of information. So if it's not relevant to your case, then it's safe to ignore it. So yeah, so all these, the rest of the code is basically the same as it was in CUDA. So as you can see, like, the reviewing part is a part where it takes a bit of time. There is also this diagnostic reference. It is basically a bunch of diagnostic information. It gives you a bunch of information of what all these warnings are and how it can be tackled. So I highly recommend you to go through that. If you are currently using DPCT and if you don't know what these errors or what these warnings are, then this gives you a comprehensive uh, dump. Yeah, so that's all I had for the demo part. Was there any question?
We don't have anything right now in the Q&A window.
Okay. So let me go back to the slides then.
We only have about 3 minutes left here.
Okay.
So you can use the time, yeah.
Okay, I just have 2 more slides. That's all. Um, So yeah, I just went through this in the demo, so it's all also in the slides. You can go over these. It's the same, basically the same thing. Okay, so yeah, I also spoke about the diagnostic message article. So there are a bunch of other things which might need a code review. We covered just 3 or 4 of them, but for example, if you are using a hardware dependent API in the code like clock or use of CUDA unbound template library, then in those case manual intervention will be needed. And in some cases, there are some missing features in the data parallel C++ compatibility tool. For example, the texture memory API is still currently in progress. So yeah, so some things which are currently, which might need rewriting your code. So generally, best known methods is basic. We always recommend a clean project. So always remember to use a make clean. If you don't do a make clean, then your compilation command is basically does not run anything, and it kind of give the JSON file is empty. So always do a make clean and then intercept build make. And then if migrate, it's always recommended to migrate incrementally. So initially, as we saw in the Rodinia benchmark suite, you saw a bunch of warnings. So if you're doing it over a multiple projects, then you could see a long list of warnings. So basically, that could be a little overwhelming. So it's always better to do one by one. And if you are using an IDE, then you can either use Eclipse or Visual Studio. There are other best known practices which are again covered in this article. So yeah, that's the only thing, that's the only slides which I had. Now, questions.
There's nothing in the Q&A at all, but you've done an excellent job today, Varsha, and I think we should probably get close to wrapping it up here. But thank you everybody for your attendance today. Steve, do you have some parting comments? Varsha, great job. Thank you.
Thank you, everybody. So yeah,
Yes,
please let me know if you have any questions. Just you can mail them to Jeff.
Yep, and please feel free to follow up, especially on the FPGA questions. We get a lot of questions right now that I need to get a little assistance from another department with.
Thanks a lot, Varsha. And if you need the link again to the seminar series, this one will be uploaded sometime in the next 24 hours, tinyurl.com/Stanford-1API. Thanks, everyone, and we'll see you next week.
Great. Thank you very much for hosting this, Steve. Take care.
Sure.
Thank you. Bye.